Very good morning. This is Karthik from SRM IST Vadapani campus. The title of my paper is Emulating SOCs for Accelerating Pre-Silicon Validation, and these are the outlines. So the objective of my paper is to present an efficient parallel simulation of high-level specification of the system written in any language like RTL or C or C++ by providing a systematic way to accelerate the computationally intensive part of an algorithm by a technique called profiling and thus reduce the overall time taken. So what motivated me to take up this work is even a small bug found later will cost human lives, and also the of amount invested for fabricating that particular IC. So 3 in 5 chip designs reported first time was wrong, and this mainly due to that 43 percentage of the error found was due to functional logic. So the goal of his paper is to efficiently perform pre-silicon validation of various industrial benchmark design on an heterogeneous board called Xilinx Zinc SoC, with the focus on achieving shorter simulation time, and uh, and also we'll be dealing with how efficiently we are going to simulate the various application onto this particular board. And why verification is important? Definitely 70% of your development cycle depends on this verification. And every approach to reduce this time has an overall impact on that particular product. So let us see what is meant by logic simulation or verification. It is actually done before fabrication for verifying your design. And larger the design, the more the simulation time. Primarily, you have two reasons for that. One reason is more the test vector, more the time taken. For example, if the number of test vector is 50, so if you see 2 power 50, and even if one test vector takes 1 millisecond, 2 power 50 test vectors takes 2 million years to simulate the design. So this diagram just to show you the various abstraction levels of any design. This is the very basic methodology we follow for simulating or verifying a design, where you have a design or a netlist where you apply some test vectors and you do comparison with the responses, and you want to make any change you can. This is very basic methodology. Another technique is the formal verification technique, which needs more complex mathematical procedures in order to verify your design. And there are limitations of formal verification. For example, there can be errors in specification and incomplete functional coverage of the specification, and some bugs in this verification too. So these are the various previous technique used for simulation, distributed simulation, and simulation which uses parameter library, and which uses boards like NVIDIA CUDA processor, and domain partitioning, functional partitioning. So these were the various simulation technique used before. And the issues with that particular techniques are with respect to design partitioning, and with respect to the communication and synchronization between the partitions, and also the application of parallel simulation on larger designs. So the reason, very good reason behind choosing the SOC board is that this particular the SOC what I've taken, the Zinc, as both an FPGA, that is the hardware, and the ARM processor, which is the processing section, which are fabricated in a single IC, and that board is called the Zinc processor. And the main reason for choosing that particular board is you can go for hardware acceleration, peripheral customization, and components and cost reduction, and also the component obsolescence mitigation. This is the main methodology or approach I have used. So the application will be partitioned first into hardware and software, and I'll be using two different tools like Vivado, mainly for going for the hardware development, and the software design kit SDK tool for software development, and finally we do what you call as core simulation. So the initial step in the hardware software code design is first you need to find out which part of your algorithm takes much more time. So that can be mapped into an hardware. So that technique is called as the profiling technique, and and this is the board that we are going to use for the entire methodology that we follow. And main probably uh, profiling is a technique which allows you to find a program that you have written consumes more time, and that function can be mapped into the programmable logic part of that particular board. So output of the profiling is what you get is with respect to the time consumed for every function. So if you see the function name open takes 33.34 section. So that particular function can be mapped into the programmable logic of that particular zinc board. So these are the various parameters of profiling technique. And the tool that I've used for the entire design is the Vivado tool. And you have an high-level compiler, a simulator, and IP integrator. And this is the implementation flow. You can go to create an Vivado project, and you're going to create the necessary hardware and the IPs, and you're going to build the project and going to uh, export to the Xilinx XDK, where you're going to create the standalone BSP and board support packages and application project. And finally, you can do the profiling and find out which function to be mapped into the hardware section. And you're going to create a custom IP out of it, integrate it, and you're going to use the entire disk bench to simulate the entire design on the Zinc board. So this is the creation of Zinc hardware, and this is the board that I've used. So this is how the profiling is being done, and the function which consumed time, the IP was created for it, and that was integrated to the rest of the design. And these are the various benchmark design that I've taken and used my methodologies for ALU, for encryption algorithm, and for a PCI bus. And this is the speed up simulation speed up for various circuit design. I have compared with the existing simulation design, and the simulation time taken by the methodology and the corresponding speed up factor is shown. This is a conclusion. So we can see that the total time taken by the each function can be analyzed following by the transfer of the timing consuming function on the hardware and accelerating the verification. And these are the references that I have used. Thank you.